A galaxy can spend billions of years building itself only to reach an age when almost no new stars are born. Long before that quiet ending, dark matter gathers the first gas, young stars ignite, spiral disks take shape, black holes grow, and entire galaxies collide, merge, and consume smaller neighbours. Yet the strangest part may be the final transition. Some galaxies still contain cold gas even after star formation has nearly stopped. If calm space science makes these long peaceful journeys worth returning to a like subscription or share, help support more thoughtful science stories like this one. And wherever this finds you, leave a comment with your city or country, and the time there, whether this is playing before sleep during work or in a quiet room far into the night. Thank you for spending part of your time here. Now the story moves backward beyond every spiral and star to the faint cosmic seeds from which the first galaxies began to grow. Before there are galaxies, before there are stars, and long before planets can gather around them, the universe already contains the faint beginnings of structure. The early cosmos is not perfectly smooth. Matter and radiation are spread with extraordinary uniformity, but not with absolute precision. Tiny differences in density exist from place to place, slight excesses and slight deficits, imprinted when the universe is still extremely young. These variations are small enough that at first they do not resemble objects at all. They are not clouds, clusters, or visible formations. They are only statistical irregularities in an expanding universe. Yet gravity is patient, and those small irregularities are enough. Regions containing slightly more matter pull a little more strongly on their surroundings. Over time, they gather additional material, deepen their gravitational influence, and begin the slow transformation from nearly featureless conditions into the first framework of cosmic structure. This process depends heavily on dark matter, an invisible component that does not emit or reflect light, but reveals itself through gravity. Ordinary matter made of the particles that later form gas stars, planets and living systems interacts with radiation and can lose or gain energy through collisions. Dark matter behaves differently. It does not couple to light in the same way, so it can begin assembling gravitational structures without being held back by the pressure of radiation to the same extent as ordinary gas. As the universe expands and cools, dark matter collects into increasingly pronounced concentrations known as halos. These halos are not solid shells. They are extended regions in which dark matter density is higher than average, creating gravitational wells that can attract ordinary matter. In this sense, the first future galaxies are shaped by something that cannot be seen directly. Their earliest architecture begins not with stars but with invisible gravity. The significance of this becomes clearer after the universe cools enough for electrons and atomic nuclei to combine into neutral atoms. Before that transition, free electrons scatter light efficiently, and the cosmos behaves like a hot opaque plasma. Once neutral hydrogen and helium form radiation can travel much more freely. The afterglow of that transition survives as the cosmic microwave background, carrying a record of the small density differences that already exist. The variations visible in that ancient radiation are subtle, but they are not meaningless noise. They are the early pattern from which much larger structures eventually develop. Gravity amplifies what is initially faint. A slightly denser region becomes more attractive to surrounding matter. As more matter falls inward, the region becomes denser still. The process is slow at first, then increasingly effective as the contrast grows. Dark matter halos merge with other halos, smaller structures combine into larger ones, and a branching hierarchy of gravitational assembly begins to take shape. None of this happens in isolation from cosmic expansion. The universe continues to grow larger, while gravity works locally against that expansion. Most regions simply move farther apart, but where matter is concentrated enough, gravity can overcome the local tendency to disperse. These bound or nearly bound regions become the sites where gas can accumulate. Ordinary gas does not simply fall straight to the center and remain unchanged. It heats as it enters deeper. Gravitational wells collides with other gas radiates energy and gradually settles into denser configurations. In the earlier small halos, this process is limited by how efficiently primordial gas can cool. The first cosmic gas is chemically simple, composed mostly of hydrogen and helium with only trace amounts of a few lighter elements. It lacks the heavier elements that later make cooling more efficient. Even so, under suitable conditions, the gas can lose enough energy to contract further. The deeper it falls, the more its future becomes tied to the halo around it. The invisible structure supplies the gravity. The gas supplies the material from which luminous structure can later emerge. This distinction matters because galaxies do not begin as isolated collections of stars appearing from nowhere. They arise from the interaction between dark matter, ordinary matter expansion, cooling, and gravity across enormous spans of time. The first stage of galactic life is therefore not a visible birth, but a long preparation. Matter must first be gathered into the right gravitational environments. Gas must become concentrated. Density differences must grow beyond their nearly imperceptible initial state. The conditions for stars must be assembled before stars themselves can exist. In modern cosmology, much of this large-scale development is described by models in which dark matter provides the dominant gravitational scaffolding on galactic and larger scales. Computer simulations based on these models show networks of filaments, sheets, knots, and voids emerging as gravity magnifies the early density field. Matter flows toward denser regions, and the most significant concentrations develop where filaments intersect. These patterns form what is often called the cosmic web. The name can suggest a finished structure, but in the early universe it is better understood as an evolving distribution, one that becomes more pronounced as time passes. Future galaxies tend to arise in its denser parts, where halos are fed by surrounding matter, and where repeated interactions can eventually become common. The earliest galactic seeds are therefore not evenly scattered. Their growth is connected to their location within this developing network. Some halos remain small, others gather matter more rapidly. Some merge early and often, others evolve in quieter environments. The differences that later produce a wide variety of galaxies begin partly in these early gravitational circumstances. Even before a single mature galaxy exists, future diversity is already being prepared by differences in mass-environment merger history and access to gas. There is still no clear boundary at this stage separating a future galaxy from the larger structure surrounding it. Halos overlap, combine, and accrete material continuously. The word seed is useful only if it does not imply a tiny finished object waiting to enlarge. What exists instead is a set of initial conditions and growing gravitational structures from which galaxies can emerge. The process is dynamic from the beginning. Matter streams inward, halos collide, gas shocks and cools. Shocks. Small concentrations disappear into larger ones. The architecture of later cosmic history is already being rewritten by countless mergers, too early and too faint to be observed in the ordinary visual sense. This makes the first chapter of galactic evolution fundamentally different from later ones. A mature galaxy can be described by its star's gas-dust shape, color, black hole, and rate of star formation. None of those familiar features defines the beginning. At first, there is only structure becoming possible. The universe is moving from smoothness toward contrast, from slight density differences toward bound regions, from diffuse matter toward concentrations capable of supporting the first luminous systems. That transition is not a single event. It unfolds continuously as gravity strengthens the differences that expansion does not erase. The remarkable part is that galaxies inherit this ancestry even after it becomes invisible. A spiral disk billions of years later may appear to be defined by bright stars and sweeping arms, yet its existence still depends on a dark matter halo whose lineage extends back to these early concentrations. A giant elliptical may contain ancient stars whose motion seem detached from any simple disk, but it too is built within the legacy of repeated halo growth and merger. Even the large clusters that eventually hold hundreds or thousands of galaxies grow from the same principle. Small density excesses become larger structures because gravity gives them time to accumulate matter. The universe does not need a dramatic beginning for each object. It needs only unevenness, gravity, and time. What begins as a barely measurable contrast can eventually become a place where billions of stars are bound together. That is the quiet power of the first galactic seeds. They are not galaxies yet, and they do not shine. They are patterns in matter deepening wells of gravity, and channels through which gas will later flow. Their importance lies in what they make possible. Once enough ordinary matter collects inside these early halos, the conditions change. Gas can reach higher densities. Cooling becomes more consequential. Collapse can proceed on smaller scales. And within some of these first compact environments, the universe approaches a new threshold because gravity is no longer only arranging dark matter and gas. It is preparing the first places where matter can ignite. The first galaxies do not appear as complete islands of stars. They emerge gradually inside the dark matter halos that have already begun gathering gas, and their birth is less like the sudden appearance of a finished object than the moment when several slow processes finally become visible at once. Hydrogen and helium, drawn inward by gravity, collect in the deepest parts of early halos. As the gas becomes denser, it can cool more effectively, and once local regions lose enough pressure support, they begin to collapse. Within those collapsing pockets, the first generations of stars ignite. These early stars form from material that contains almost none of the heavier elements common in later stellar nurseries. The gas is chemically simple, the cooling pathways are limited, and the conditions favour stars, unlike many of those that dominate nearby galaxies today. Their exact masses and distributions remain an active subject of research, but the broader significance is clear. The first stars change their surroundings. They produce light where there had been darkness, heat, and ionize nearby gas, and begin manufacturing heavier elements inside their interiors. When some of them end their lives, those newly formed elements are returned to the surrounding medium, altering the chemistry, from which later generations of stars can form. A galaxy therefore begins not only as a gravitational structure, but as a chemical transition. The first episodes of star formation make future star formation different from what came before. In the smallest early halos, however, this process is fragile. The same stars that announce the beginning of a luminous structure can also make continued growth more difficult. Their radiation heat surrounding gas, while stellar explosions can drive material outward from shallow gravitational wells. A small proto-galaxy may begin forming stars and then lose part of the gas needed to continue. Growth is uneven. Some systems remain faint and limited, while others sit inside more massive halos that can retain gas more effectively and keep attracting fresh material from their surroundings. These differences begin to separate temporary concentrations from systems capable of sustained development. The earliest galaxies are therefore not defined by a single minimum size or by one clean moment of formation. They occupy a continuum between small star-forming structures, merging proto-galactic pieces and increasingly organized systems whose stars and gas are held within a common gravitational environment. Their appearance also depends on what an instrument is able to detect. A young galaxy can be compact, irregular, dusty, rapidly changing and dominated by only a few bright regions of star formation. The neat categories familiar from the nearby universe are not yet the most useful way to think about many of these objects. Their shapes are still being assembled, their gas is still arriving. Their stellar populations are still young, their dark matter halos are still growing through accretion and mergers. Everything important about them is in motion. This is one reason observations of the distant universe are so valuable. Light from extremely remote galaxies has travelled for most of cosmic history, before reaching modern telescopes allowing astronomy to examine the universe when these systems are still young. The James Webb Space Telescope extends that view deeper into the infrared, where light emitted at very short wavelengths by early stars and galaxies has been stretched by cosmic expansion. With that sensitivity, galaxies are being identified at times much earlier than astronomers could study in comparable detail before. Some are brighter, more massive, or apparently more developed than simple expectations might have suggested, and each new detection forces models of early galaxy formation to be tested against a growing body of evidence. This does not mean that the basic framework of structure formation has failed. It means that the details matter greatly. How quickly gas can collect, how efficiently stars form, how rapidly heavy elements accumulate, how much material early feedback removes, and how mergers contribute to growth, all influence what an early galaxy looks like at a given time. A system that appears unexpectedly bright may reflect an intense but temporary episode of star formation, rather than an impossibly mature object. A compact galaxy may build stellar mass quickly, without yet resembling a later spiral or elliptical. The observations are powerful, precisely because they begin separating these possibilities. The first galaxies also exist during a larger transformation of the universe itself. As early stars and galaxies produce energetic radiation, neutral hydrogen in intergalactic space becomes increasingly ionized. This extended transition, known as cosmic reionization, changes the state of the gas between galaxies and connects the birth of luminous systems to conditions on scales far beyond any single halo. The galaxies are not merely responding to the universe around them. Collectively, they are helping alter it. Radiation escaping from young stars travels into surrounding space, and over time enough ionized regions overlap that the intergalactic medium becomes predominantly ionized. The timing and detailed sources of this transition remain subjects of active investigation, but early galaxies are central to the story. Their influence is therefore already larger than their visible size. Inside them, stars are enriching gas with heavier elements. Around them, radiation is changing the state of hydrogen across growing volumes of space. Between them, gravity is continuing to draw halos together. The birth of galaxies is not a local event repeated in isolation. It is part of a networked phase of cosmic change. Mergers are especially important because the early universe is denser than it will be later, and growing structures encounter one another frequently. Small systems combine to form larger ones, while streams of gas continue feeding halos from the surrounding cosmic web. A young galaxy may gain mass through new star formation, direct gas accretion, and the absorption of neighbouring protogalaxies almost simultaneously. These channels blur together. New stars can form from gas that arrived smoothly from gas carried in by a merging companion or from gas compressed by an interaction. The history of one early galaxy can therefore contain several modes of growth woven into the same short interval. Over time, repeated assembly produces systems with deeper gravitational wells, larger stellar populations, more chemically enriched gas, and more complex internal structure. Yet even then, stability is temporary. The early galaxy remains dependent on a balance between supply and loss. Gas must continue reaching dense regions. Cooling must remain efficient enough for collapse. Stellar radiation and explosions can heat or expel material. The dark matter halo must be massive enough to hold on to enough of what arrives. The environment can either replenish the system or disrupt it. What later appears as a galaxy is built through this continuing negotiation between gravity-cooling star formation and feedback. The earliest observations now reveal that this negotiation can proceed quickly. Within a comparatively short span after the beginning of cosmic history, luminous systems already exist, and some contain enough stars to demand efficient growth. That speed is one of the reasons the first galaxies remain scientifically important. They test not only when galaxies begin, but how rapidly complex structure can emerge from simple initial conditions. The answer depends on processes operating across very different scales. Dark matter organizes mass over enormous regions. Gas physics determines whether material can cool into dense clouds. Star formation converts part of that gas into luminous objects. Stellar feedback redistributes energy and matter. Mergers combine what separate halos have already built. Radiation then escapes and changes the wider environment. None of these processes alone creates a galaxy. The galaxy is the outcome of their interaction. By the time a young system becomes bright enough to be recognized across immense cosmic distance, much has already happened inside it. Gas has fallen inward. Stars have formed and in some cases already died. Heavy elements have begun spreading. Neighboring structures may have merged. Fresh material continues to arrive. The object is young only in comparison with the later universe. Internally, it may already contain several generations of change. This gives the first galaxies a peculiar place in cosmic history. They are both beginnings and products. They are the first durable luminous structures on galactic scales, yet each of them is already built from an earlier history of collapse cooling and assembly. Their emergence marks the point at which the invisible framework of the universe becomes filled with persistent light. But birth does not bring completion. Once a galaxy exists, gravity does not stop drawing material inward, and the surrounding cosmic web does not stop supplying new gas and smaller companions. The first galaxies are not finished objects entering a quiet adulthood. They are open systems at the beginning of a much longer process, and nearly everything that will later define their size, brightness, chemistry, and shape still depends on what they are able to gather next. A young galaxy survives only by remaining connected to what lies beyond it. Its stars may be the most visible part of the system, but the material that determines its future often begins far outside the bright central regions, moving gradually through the surrounding halo before reaching the places where new stars can form. Galaxies do not emerge with their final mass already assembled. They grow by feeding drawing matter from the cosmic environment, while also absorbing smaller systems that have followed their own histories of collapse and star formation. The process is continuous enough that the boundary between a galaxy and its surroundings is less absolute than it first appears. Gas can enter from the larger cosmic web, circulate through the halo, cool toward the central regions, be converted into stars, be expelled by stellar activity, and sometimes return again. At the same time, satellite galaxies orbit, lose material, and occasionally merge with the larger system. Growth is therefore not a simple inward flow. It is a cycle of acquisition, redistribution, loss, and reaccretion, with gravity shaping the overall direction, while temperature, density, motion, and feedback determine how much of the incoming material actually becomes part of the visible galaxy. In the early universe, this supply can be especially important because galaxies are embedded in dense networks of matter, filaments of the cosmic web channel gas toward dark matter halos, and some of that gas can remain relatively cool as it travels inward. Rather than being heated immediately to the full temperature associated with the halo, it can penetrate in narrower streams and reach regions where star formation becomes possible. This kind of accretion offers a direct route by which a growing galaxy can maintain a supply of fresh material. The exact behavior depends strongly on halo mass, cosmic era, and environment, because gas falling into a deeper gravitational well may be shocked and heated before it can settle. In more massive halos, incoming material can form a hot diffuse atmosphere that must cool before it contributes efficiently to new stars. In smaller or earlier systems, colder inflows can be more prominent. The difference matters because a galaxy rich in stars but poor in replenishing gas cannot continue forming stars indefinitely. Stellar populations consume part of the cold material available to them, while energetic processes can move another fraction out of the dense regions where stars are born. Continued growth therefore depends not only on how much gas a galaxy contains, but on whether new gas can keep arriving, and whether that gas can lose enough energy to join the star-forming reservoir. This creates a moving balance between supply and consumption. A galaxy may enter a period in which inflow is strong and star formation rises. Later, feedback may heat or expel enough material to reduce that activity. Still later, recycled gas or fresh accretion may restore part of the supply. The life of a galaxy is shaped by these changing rates rather than by a single permanent condition. Even the gas expelled from the central regions is not necessarily lost forever. Supernovae and stellar winds can push material outward into the surrounding halo, enriching it with heavier elements produced inside stars. If that gas does not escape the gravitational influence of the system completely, it may cool and return. This circulation creates what is sometimes described as a galactic fountain, a repeated movement in which matter leaves the star-forming disk and later falls back. The returning gas is different from the primordial material that first built the galaxy. It carries elements such as carbon, oxygen, silicon, and iron products of earlier generations of stars. As a result, growth also becomes chemical evolution. A galaxy is not simply adding mass. It is repeatedly processing matter, mixing newly arrived gas with material altered by previous stars and changing the composition of the next generation. The growth of a galaxy can therefore be recorded in the metallicity of its stars and gas, where metallicity refers to the abundance of elements heavier than hydrogen and helium. Older populations often preserve the chemistry of earlier, less enriched conditions, while younger stars may form from gas that has passed through multiple cycles of stellar birth and death. The pattern is not perfectly simple, because mergers can introduce stars and gas with very different histories, but that complexity is itself part of the evidence. A large galaxy can contain populations that did not all form in the same place. Some stars are born within its main body. Others arrive already formed inside smaller companions. This second pathway growth through mergers is built into the hierarchical structure of cosmic evolution. Dark matter halos combine over time and the galaxies inside them are drawn into the same gravitational process. When a smaller system falls toward a larger one, it does not disappear immediately. It can orbit for a long period while tidal forces stretch it, remove gas and strip away stars. Its orbit gradually changes as gravitational interactions transfer energy and momentum through the surrounding matter. Eventually, some satellites merge with the central galaxy, adding their star's gas, dark matter, and sometimes their central black holes to a larger system. A major merger involving galaxies of more comparable mass can transform structure dramatically. A minor merger may appear less disruptive, yet repeated minor events can still build a substantial fraction of a galaxy over time. This means that galactic growth occurs both from within and from outside. New stars formed from accreted gas increase the galaxy's mass internally, while already existing stars brought in by companions increase it externally. These two forms of growth can leave different signatures. Stars formed in the central regions may follow the chemical and dynamical history of the main galaxy, while accreted stars can remain in extended halo streams or distinct orbital structures long after their original galaxies have been disrupted. The larger the system becomes, the more complicated this ancestry can be. What appears to be one galaxy may contain material assembled from many earlier ones. Growth also changes the galaxy's ability to keep growing. As the dark matter halo becomes more massive, its gravitational well deepens, allowing it to retain more material. Yet greater mass can also make infalling gas hotter, lengthening the time needed for that gas to cool. A galaxy can therefore enter a regime in which the same halo that once helped gather fuel increasingly surrounds the system with a reservoir that is difficult to turn into stars. This tension becomes important later in galactic evolution, when the question shifts from how galaxies gain material to why some of them stop using it efficiently. At this stage, however, the dominant impression is one of openness. Matter is still arriving from many directions and in many forms. Cold gas follows filaments, hot gas settles through the halo. Recycled material falls back after being expelled. Satellites bring stars that formed elsewhere. Mergers rearrange angular momentum and redistribute gas. The galaxy grows not as an isolated city adding buildings within fixed walls, but as a changing gravitational system whose borders are crossed constantly. Even angular momentum, the tendency of matter to maintain rotational motion, is affected by this feeding history. Gas rarely falls directly inward without sideways motion. It arrives with angular momentum inherited from the larger structure around the halo, and as it settles, that motion can help produce rotating disks. Mergers can then alter, reinforce, or disrupt those ordered patterns. A galaxy's eventual shape is partly connected to how its material was acquired, not merely to how much was acquired. Smooth gas inflow can help sustain disk growth, while repeated interactions can thicken or disturb that disk. Major mergers can redirect stellar orbits and erase much of the previous organization. In this way, feeding begins to connect mass growth with morphology, the visible form a galaxy will later display. The rate of accretion also changes across cosmic time. The early universe provides abundant material and frequent interactions, allowing many galaxies to grow rapidly. As cosmic expansion continues, and available gas becomes more diffuse or locked into existing structures, typical growth rates decline. Galaxies do not all follow the same schedule, however. Environment, halo, mass, merger history, and feedback create enormous variation. Some systems gain mass steadily, others experience bursts of growth separated by quieter intervals. Some remain small for billions of years. Others become the dominant galaxies of groups and clusters, accumulating satellites long after their most intense periods of star formation have ended. There is no single route from protogalaxy to mature system. What unites these histories is dependence on exchange with the surrounding universe. Every star formed requires matter that once came from somewhere else. Every merger carries an earlier record into a new gravitational home. Every halo is part of a larger hierarchy of structure. The apparent individuality of a galaxy is real, but incomplete. Its mass, chemistry, motion, and future are inseparable from the flows that have crossed its boundaries. As gas continues to arrive and stellar populations expand, one consequence becomes increasingly important. A galaxy that can maintain a rich supply of cold, dense material does more than grow quietly. It can enter periods when star formation accelerates, filling its disk or central regions with young luminous stars at a rate far above its ordinary level. Feeding has built the reservoir. The next transformation depends on how rapidly that reservoir can be turned into light. A galaxy can accumulate gas for a long time without looking dramatically different from one moment to the next, but when enough of that material becomes cold, dense, and unstable, the character of the system begins to change. Clouds contract under gravity. Smaller concentrations develop inside larger ones, and some of those dense regions reach the conditions needed for new stars to form. Star formation is therefore not simply the presence of gas. It depends on gas becoming concentrated enough for gravity to overcome the pressures and motions that otherwise keep it dispersed. In a gas-rich galaxy, this can happen across many regions at once. The result is a population of young stars appearing throughout a disk within crowded central zones or inside disturbed structures shaped by previous interactions. These stars alter the galaxy almost immediately in appearance. Young massive stars radiate strongly and can make star-forming regions unusually bright. While the surrounding gas and dust respond to the energy released by those new stellar populations, a galaxy that was once defined mainly by the slow accumulation of material now becomes a place where that material is being transformed. Gas is not merely entering the system, it is being converted into stars, and the rate of that conversion becomes one of the most important signs of the galaxy's current state. Some galaxies form stars at modest rates for long periods. Others pass through episodes in which star formation rises far above their usual level. These systems are commonly described as starburst galaxies, and the term reflects a real change in tempo. A starburst does not mean that every part of a galaxy forms stars equally, or that the enhanced activity can continue indefinitely. It means that for a period the conversion of available gas into stars becomes unusually intense compared with the galaxy's more ordinary behavior. Such episodes can occur when a galaxy contains a large reservoir of cold gas, and when that gas is driven into denser configurations. The same gravitational processes that help galaxies grow can also create these conditions. Incoming material increases the fuel supply. Interactions can disturb otherwise stable gas. Collisions between gas-rich systems can compress material and concentrate it in regions where star formation becomes more efficient. The exact path differs from one galaxy to another, but the consequence is similar. More gas reaches the dense state needed to produce stars over a shorter interval of time. The galaxy brightens, its stellar population becomes younger on average in the active regions, and its future chemical and structural evolution begins to accelerate. This intense activity also explains why star formation cannot be understood as a one-way conversion from gas into stars. New stars change the environment that created them. The most luminous young stars release large amounts of energy into nearby material, while the deaths of massive stars return matter to the surrounding gas. That returned material can later participate in further generations of star formation. The galaxy is therefore both a factory and a recycling system, though neither process is perfectly efficient. Some gas remains diffuse, some is heated, some is displaced, some is eventually reused. What matters during a strongly star-forming phase is that the cold reservoir remains large enough, and dense regions continue forming quickly enough for stellar birth to remain vigorous. Over time, this activity begins to write itself into the galaxy's light. A population dominated by very young stars does not shine in the same way as a population dominated by older stars. Massive young stars are extremely bright and contribute strongly to the blue and ultraviolet light associated with active star formation. Because such stars do not live for as long as lower mass stars, their presence is evidence of relatively recent stellar birth. If star formation continues, new luminous stars keep replacing those that disappear. The galaxy can therefore retain a bluer appearance in the regions where stellar birth remains active. If the formation of new stars later declines, those short-lived bright stars fade from the population first, and the balance of the galaxy's light shifts. In this way, colour becomes connected to history. It is not a simple label attached permanently to one type of galaxy. It reflects in part the ages of the stars currently contributing most strongly to what is observed. Brightness also carries history, although it is shaped by many factors at once. A starburst can make a galaxy or one of its regions extraordinarily luminous, because so many young stars are present at the same time. Yet high brightness does not automatically mean that the galaxy contains more total stellar mass than every quieter system. A comparatively brief period of intense star formation can temporarily make a galaxy stand out, because young massive stars contribute so much light. This distinction becomes important when astronomers compare galaxies at different stages of evolution. A bright galaxy may be caught during an active phase, while a less conspicuous system may contain an enormous older stellar population whose most luminous members disappeared long ago. The visible state is therefore a moment within a longer life cycle. The same is true of starbursts themselves. They are not a permanent identity. Intense star formation consumes part of the cold gas reservoir, while the energetic activity associated with young stars can alter the conditions in which further stars would otherwise form. If fresh gas continues to arrive, activity may be sustained or renewed. If the supply weakens, the burst cannot simply continue at the same pace forever. This gives star formation a natural rhythm across galactic history. Periods of strong activity can be followed by calmer intervals, and those calmer intervals can later be interrupted by new accretion or interactions. A galaxy may therefore pass through several distinct star-forming phases without ever repeating exactly the same conditions. Each phase leaves behind a population of stars with its own age and chemical history. As these populations accumulate, the galaxy becomes a layered record of its own past activity. Older stars preserve earlier episodes. Younger stars trace more recent ones. The total light combines all of them, so the appearance of a galaxy at any moment is the blended result of many generations rather than the signature of a single event. This cumulative character becomes especially important as galaxies become larger and more complex. A region that is actively forming stars may sit beside another dominated by older populations. One part of a disk may be rich in cold gas, while another has already converted much of its dense material into stars. Central regions can behave differently from outer regions. A merger can trigger concentrated star formation in one phase and leave a more diffuse stellar system later. The idea of a galaxy as one uniform stellar factory is therefore misleading. Star formation is distributed unevenly through both space and time. What makes an active galaxy remarkable is not uniformity, but the scale on which many local star-forming processes are occurring together. The broader universe changes as well. In earlier cosmic eras, many galaxies have access to abundant gas and can build their stellar populations rapidly. Across time, these repeated episodes of stellar birth transform diffuse matter into long-lived stars and stellar remnants, while enriching the remaining gas with elements produced by earlier generations. Galaxies become brighter, more chemically complex, and increasingly structured by the populations they have already formed. The stars themselves begin to dominate what is visible, but the gas still controls what can happen next. A galaxy rich in cold gas retains the possibility of continued renewal. A galaxy that loses access to that state begins moving toward a different future. This is why the great star-forming phases are more than periods of high luminosity. They are turning points in the conversion of a galaxy's raw material into the stellar populations that will define it for billions of years. They determine which parts of the galaxy remain blue with recent activity, which parts begin aging, and how quickly the system builds its luminous mass. Yet even while stars are being born at extraordinary rates, another transformation is taking place more quietly. The material is not only becoming brighter, its motion is becoming organized, disturbed, or redirected. Disks can settle, interactions can thicken them, mergers can erase earlier patterns. The same history that controls star formation is also beginning to determine the shapes galaxies will eventually carry, turning the record of stellar birth into a record written across structure itself. A galaxy's shape is not an ornament added after its stars are formed. It is a record of motion. Long before a spiral arm becomes visible, gas and stars are already carrying angular momentum, responding to gravity, losing energy, being scattered, and settling into patterns that can persist for billions of years. In many young systems, gas arriving through the surrounding halo does not fall straight toward the center. It carries sideways motion inherited from the larger structure around the galaxy, and as the material loses energy without losing all of that angular momentum, it can settle into a rotating disk. Within such a disk, stars form from dense clouds that share the overall rotational motion of the gas. Over time, the disk becomes a broad, flattened stellar structure in which much of the motion is ordered around a common center. This is the foundation of the spiral galaxy, but the familiar spiral pattern is not simply the shape of the disk itself. Spiral arms are regions where stars, gas and dust become organized into enhanced structures within the rotating disk, and their exact origin can involve several processes. Gravitational disturbances, internal instabilities, and interactions with nearby galaxies can all help produce or maintain spiral patterns. Some arms behave more like long-lived density patterns through which stars and gas move, while others are more transient features that form change and fade. What matters for the life of the galaxy is that the disk remains dynamically cold enough for ordered rotation to dominate over random stellar motion. In this context, cold does not refer only to temperature. It describes a system in which stars move in relatively coordinated orbits, rather than with large random velocities in many directions. A thin stellar disk can therefore survive only if it avoids too much gravitational disturbance. Small interactions can heat it, meaning that stellar orbits become more disordered and the disk thickens. Repeated encounters can gradually turn a delicate structure into a broader, more dynamically mixed one. The central regions can evolve as well. Many disk galaxies develop a bulge, a denser concentration of stars around the center, and some also form elongated bars that extend across the inner disk. A bar can redistribute angular momentum and help move gas inward, where it may support central star formation or feed activity closer to the galactic nucleus. These structures show that morphology can change even without a major collision. A galaxy can reorganize itself through internal gravitational processes, slowly shifting the arrangement of stars and gas while remaining recognizably the same system. Elliptical galaxies represent a different dynamical state. Rather than being dominated by a thin rotating disk, many contain stars moving on a wide variety of orbits, producing a smoother, rounder, or more elongated appearance. Their stellar populations are often older on average, and they usually contain less cold star-forming gas than actively star-forming spirals, though these tendencies are not absolute rules. The important distinction lies in the orbital structure. Inner disk rotation provides much of the support against gravitational collapse. In an elliptical system, random stellar motions play a larger role. The stars are still bound by gravity, but their paths are less organized into one common plane. Such a configuration can emerge through violent gravitational events, especially mergers that disturb or destroy pre-existing disks. When two substantial galaxies interact, their stars usually do not collide directly, because the distances between individual stars are enormous compared with stellar sizes. Instead, the overall gravitational fields change rapidly, altering stellar orbits on a large scale. Gas behaves differently because gas clouds can collide, shock compress, and lose energy. The same merger can therefore scramble existing stars while driving gas toward denser regions. After the encounter settles, the remnant may have little resemblance to either original disk. This is one path toward building an elliptical galaxy, particularly in major mergers, although the full population of elliptical systems reflects many formation histories and cannot be reduced to a single event. Dwarf galaxies add another layer of complexity. These small systems can be irregular spheroidal disk-like, or something between familiar categories. Their shallow gravitational wells make them especially sensitive to stellar feedback and environmental effects. Gas can be lost more easily, star formation can proceed in intermittent episodes, and interactions with larger neighbors can strongly reshape them. Some dwarfs preserve relatively simple histories, while others show evidence of repeated disruption. Because large galaxies grow partly by absorbing smaller systems, dwarfs are not merely minor variations at the edge of galactic classification. They are participants in the larger assembly process, and may resemble the kinds of building blocks that contributed to bigger galaxies in earlier eras. Irregular galaxies demonstrate even more clearly that galactic shape can be temporary. Some lack a stable spiral pattern or smooth elliptical structure because they are small and dynamically unsettled. Others have been distorted by interactions, mergers, or intense star formation. Their appearance can include asymmetrical clumps, displaced star-forming regions, and streams of material extending away from the main body. Calling such a galaxy irregular describes its current structure, not its permanent destiny. It may later settle into a more ordered configuration, merge into a larger system, or continue changing as new material arrives. The traditional categories of spiral, elliptical, and irregular are useful because they capture broad differences, but real galaxies occupy a continuum. Lenticular galaxies, for example, have disk-like structures but relatively little obvious spiral activity, placing them between the familiar visual extremes. Some galaxies contain rings, warped disks, multiple components or features inherited from previous encounters. The deeper the observations become, the harder it is to treat morphology as a small set of rigid boxes. Instead, shape becomes a snapshot of several competing processes acting together. Gas supply matters because it determines whether a disk can continue forming young stars and maintaining bright spiral structure. Angular momentum matters because it controls how material settles and rotates. Internal instabilities matter because they can build bars, bulges, and other features without an external collision. Environment matters because neighboring systems can pull on a galaxy strip material or trigger interactions. Merger history matters because sufficiently strong encounters can reconstruct the entire orbital arrangement of the stars. Even the dark matter halo matters because its gravitational field helps set the larger potential in which the visible galaxy evolves. Morphology is therefore not independent of the galaxy's hidden mass or its feeding history. It is the visible consequence of all of them working together. This also means that two galaxies with similar shapes can have different pasts. One disk may have grown quietly through long-term gas accretion, while another may have rebuilt a disk after earlier disruption. One elliptical may be the remnant of a major merger, while another may have accumulated its structure through repeated smaller events and long internal evolution. Appearance alone cannot reveal every step. Astronomers therefore combine morphology with stellar ages, chemical composition, gas content, stellar motions, and the presence of streams or shells to reconstruct galactic history. These clues turn shape into evidence rather than classification alone. A thickened disk may preserve the memory of past heating. A faint stellar stream may reveal a disrupted satellite. A central bulge may record both internal evolution and earlier mergers. A bar may show that angular momentum is still being redistributed. The galaxy carries its history in the way its matter moves. This is why morphology can evolve even after the most obvious event has ended. A merger may last for a comparatively short interval, but the altered orbits it produces can define the remnant for billions of years. A burst of gas accretion may build a disk that continues rotating long after the inflow weakens. A satellite encounter may leave a warp or stream that survives as a faint signature of the disturbance. Shape is therefore accumulated memory, constantly revised but rarely detached from what came before. Yet visible form is only part of the structure holding a galaxy together. The stars may trace a disk bulge or diffuse elliptical body, but their motion often points to much more mass than the luminous material alone can provide. The outer parts of galaxies move within gravitational fields that extend far beyond the bright stellar boundaries, and the architecture that governs those motions is dominated by something that cannot be seen directly. The next layer of galactic structure is therefore not another visible shape, but the invisible halo surrounding it. The visible edge of a galaxy is not the edge of its gravitational influence. Beyond the bright disk of a spiral, beyond the diffuse light of an elliptical, and far outside the regions where most stars can be counted easily. gravity continues to act as though a much larger reservoir of mass is present. This extended influence is one of the clearest reasons dark matter occupies such a central place in modern models of galaxy formation. The stars, gas, and dust that produce nearly all of a galaxy's light account for only part of the mass needed to explain how many galaxies move and remain bound. Surrounding the luminous structure is thought to be a much larger dark matter halo, an invisible distribution whose gravity affects everything from the motion of stars to the way fresh material approaches the galaxy. The halo cannot be photographed in the ordinary sense because dark matter does not appear to emit, absorb, or reflect light in the ways familiar matter does. Its presence is inferred through its gravitational effects. In disk galaxies, one important clue comes from the orbital motion of stars and gas. If most of the mass were concentrated only where the visible matter is brightest, orbital speeds would be expected to decline more strongly at large distances from the center. Instead, measurements in many galaxies indicate that outer material continues moving faster than the luminous mass alone would suggest. The simplest interpretation within the prevailing framework is that substantial unseen mass extends well beyond the stellar disk. This invisible halo changes the scale of the galaxy. What appears through a telescope as a luminous island is embedded inside a far larger gravitational structure. The same principle helps explain why dark matter was already important before the first galaxies formed. The halo is not merely an extra component added around a mature galaxy. Its history is intertwined with the galaxy from the beginning. Early dark matter concentrations create gravitational wells into which ordinary gas can fall. As halos grow through accretion and mergers, they provide the larger framework within which visible galaxies assemble. In this sense, the galaxy of stars is only one part of a broader system. The luminous structure reveals where much of the cooled ordinary matter has collected, while the dark halo preserves a larger record of gravitational growth. This distinction becomes especially important when considering how galaxies continue to acquire material. Gas approaching a galaxy first encounters the gravitational influence of the halo, not simply the stars at the center. The depth and extent of that halo help determine how strongly material is captured, how hot in falling gas may become, and whether expelled gas is likely to escape completely or remain bound to the system. A more massive halo can hold material more tightly, but greater mass can also create conditions in which gas is heated and remains diffuse, rather than cooling rapidly into the star-forming regions. Dark matter therefore influences galactic growth without directly participating in star formation itself. It shapes the gravitational environment in which ordinary matter must operate. The halo also affects smaller galaxies approaching a larger one. A satellite does not respond only to the visible disk or central bulge. It moves within the total gravitational potential, most of which extends through the surrounding dark matter distribution. Its orbit can change over time as gravitational interactions redistribute energy and momentum. Tidal forces can strip stars' gas and dark matter from the satellite, gradually reducing it before a merger is complete. The larger galaxy may then absorb what remains. In this way, dark matter participates in the mechanics of galactic cannibalism long before the visible remnants become obvious as stellar streams. The same halos also merge with one another often before the galaxies inside them have fully combined. A merger between halos reorganizes the gravitational setting of everything they contain. Gas responds by heating, cooling, shocking, and flowing. Stars respond through changing orbits. Satellite systems are rearranged. The dark component passes through the encounter, according to gravity helping create a new combined halo around the eventual remnant. Because the halo usually extends much farther than the bright galaxy interaction, begins gravitationally before the luminous structures appear to touch. Two galaxies can already be altering each other's motion, while their stellar disks remain widely separated. The visible collision is therefore only the central phase of a much larger gravitational event. This hidden architecture also influences the diversity of galaxies. Halos differ in mass growth, history, concentration, and environment. A small halo may host a dwarf galaxy whose shallow gravitational well makes gas easier to disturb or remove. A much larger halo may surround a massive galaxy with a hot gaseous atmosphere and numerous satellites. Some halos grow quietly for long periods, while others experience repeated mergers. Since the visible galaxy develops inside this evolving structure, differences in halo history can contribute to differences in the galaxy itself. Yet the relationship is not simple enough to say that one halo mass automatically produces one kind of visible galaxy. Gas physics, star formation, feedback, angular momentum, and environment all matter as well. Dark matter establishes much of the gravitational framework, but ordinary matter determines how that framework becomes luminous. This separation between influence and visibility is one reason dark matter remains such an unusual scientific problem. Its large-scale gravitational role can be modelled and tested through astronomical observations, yet its microscopic identity is still unknown. The term dark matter describes the behaviour required by a wide range of gravitational evidence, but it does not specify what the substance actually is. No confirmed particle has yet provided a complete microscopic explanation. That leaves astronomy in an unusual position. Galaxies can be studied as systems whose formation and motion depend strongly on an invisible component whose underlying nature remains unresolved. The uncertainty does not make dark matter optional within the standard picture of galaxy formation. It means that the gravitational evidence and the particle-level explanation occupy different stages of understanding. On galactic scales, the unseen mass can be mapped indirectly. The motions of stars and gas provide one route. Gravitational lensing provides another because mass bends the path of light from more distant objects. In larger systems and clusters, such effects can reveal distributions of mass that do not follow the luminous material exactly. These observations reinforce the idea that visible matter is not tracing the full gravitational landscape. A galaxy's appearance may therefore be a poor guide to its true dimensions. The brightest regions can occupy only a small fraction of the volume governed by the halo. Far outside the stellar disk, sparse gas satellites and diffuse stellar populations continue moving inside the same extended gravitational domain. The halo is less like a rigid container than a gradually thinning distribution with no sharp luminous boundary. Its outer regions blend into the surrounding cosmic environment, where neighbouring halos, filaments, and larger structures exert their own influence. This makes the concept of a completely isolated galaxy even less realistic. The visible galaxy is nested inside a halo. The halo is embedded within the cosmic web, and the web itself continues to evolve. Matter can cross these nested scales over billions of years. Small halos fall into larger ones. Gas moves through filaments. Satellites circulate through extended gravitational fields. The life of a galaxy is therefore inseparable from structures much larger than the region where most of its stars shine. Dark matter also provides continuity between the earliest and later stages of galactic evolution. In the beginning, halos create the gravitational sites where gas collects. During growth, they guide accretion and mergers. In mature galaxies, they influence orbital motion and the retention of matter. During interactions, their extended structures are among the first components to overlap and combine. Even as star formation rises and falls, the halo remains a major part of the gravitational system. The visible galaxy can transform from a gas-rich disk into a quieter stellar population, yet it continues to inhabit the legacy of the dark structure that helped assemble it. What remains unresolved is why that invisible framework has the precise properties it does. The microscopic nature of dark matter has not been established, and that missing piece prevents the story from being complete at its deepest level. Still, the gravitational role of the halo gives galaxies an architecture far larger than their light suggests, and near the center of many massive galaxies, another hidden influence begins to matter on a very different scale. There, instead of an extended halo surrounding the system, enormous mass is concentrated into an extraordinarily compact region. When gas reaches that center and begins falling inward, the galaxy can release energy capable of affecting material far beyond the black hole itself. A supermassive black hole occupies almost no volume compared with the galaxy around it, yet when matter begins falling toward that compact center, the consequences can spread across distances measured in thousands of light years. In many massive galaxies, the central black hole is normally quiet enough to reveal itself mainly through the motion of nearby stars and gas. Its gravity dominates only the innermost region, while the galaxy as a whole remains governed by the combined mass of stars' gas-dark matter and the broader structure surrounding them. But a black hole does not need to dominate the entire gravitational field to influence the evolution of the galaxy. It needs only a supply of matter. Gas that loses enough angular momentum can move inward toward the center, where it forms a rapidly rotating accretion flow. Friction, turbulence, magnetic fields, and orbital motion heat that material to extreme temperatures before much of it crosses the black hole's event horizon. The energy released during this process can make the central region enormously luminous. The result is an active galactic nucleus, a compact source whose radiation can outshine much of the surrounding galaxy, even though the emitting region is tiny by galactic standards. The black hole itself produces no light from within the event horizon. The brightness comes from matter being heated and accelerated outside it. This distinction is important because the most visible phase of black hole growth is really a phase of violent activity in the surrounding gas. Some active nuclei produce powerful jets, narrow streams of energetic particles launched away from the central region and guided by magnetic fields. Others drive broader winds through the surrounding gas. In both cases, energy and momentum that originate near the black hole can be carried far into the host galaxy and sometimes beyond it. This is the basis of what astronomers call active galactic nucleus feedback. The phrase describes the ways in which energy released during black hole accretion can alter the gas from which future stars might otherwise form. The basic idea is straightforward, but its detailed consequences are not. If energy from the nucleus heats cold gas, pushes it outward, or keeps halo gas from cooling efficiently, star formation can decline. If an outflow compresses gas in particular regions, it may under some conditions contribute to new star formation instead of suppressing it. The direction and strength of the effect depend on the structure of the gas, the duration of the active phase, the geometry of the outflow, the mass of the host galaxy, and the surrounding environment. Feedback is therefore not a single switch that turns star formation off. It is a family of processes whose influence can vary greatly from one system to another. The need for some form of regulation becomes clearer when galaxy growth is compared with the enormous amount of gas that can be available. If every reservoir cooled rapidly and every dense region turned material into stars without interruption, many theoretical models would build galaxies that are too massive or too actively star-forming compared with what is observed. Energy from stars themselves provides part of the regulation, especially in smaller galaxies where supernovae and stellar winds can strongly disturb the gas. In more massive systems, however, central black holes offer another source of energy capable of reaching scales much larger than the region in which the accretion occurs. This makes active galactic nucleus feedback an important ingredient in many models of galaxy evolution. Yet importance in a model is not the same as a fully settled physical picture. Astronomers can observe fast winds, radio jets, cavities in hot gas-disturbed molecular material, and other signs that central activity is interacting with the host galaxy. What remains difficult is following that energy through every stage and determining exactly how much it changes the long-term formation of stars. A jet may inject enormous energy into a surrounding halo without coupling efficiently to the cold gas inside the galaxy. A wind may remove material from the central region, but leave a large reservoir at greater distances. Gas may be pushed outward and later fall back. An active episode may be brief compared with the timescale over which the stellar population responds. The black hole can therefore be powerful without acting as a simple executioner. Its influence is mediated by the gas, and gas can respond in complicated ways. This uncertainty becomes even more interesting because black hole growth and galaxy growth appear closely connected. The masses of central black holes correlate with properties of the stellar bulges around them, suggesting that the evolution of the nucleus and the evolution of the host are not completely independent. The correlation does not by itself prove one simple causal pathway. Both may respond to the same supply of gas, both may be shaped by mergers, and feedback may help regulate their growth over time. The relationship is likely built from several linked processes rather than one universal sequence. When a galaxy experiences an interaction, for example, gravitational torques can disturb gas and move some of it inward. That gas may fuel a burst of star formation, while another fraction reaches the central black hole. The galaxy and black hole can therefore become active during overlapping periods because they are feeding from the same disturbed reservoir. As the nucleus brightens, its outflows may then alter what remains. This creates a feedback loop. In the literal sense, the material that feeds the black hole enables the black hole to release energy that changes the conditions governing later inflow. The cycle can repeat many times. A black hole may spend long intervals in a quiet state and then enter a much brighter phase when fresh gas reaches the center. A galaxy can therefore contain an enormous central black hole without always appearing active. The active phase is episodic, while the black hole itself remains as a long-lived record of earlier feeding. Over cosmic time, repeated episodes allow the black hole to gain mass just as repeated star-forming phases allow the galaxy to build its stellar population. The two forms of growth occur on different scales, but can be driven by related events. This is especially relevant in dense galactic centers, where gas driven inward by Barr's mergers or internal instabilities may encounter increasingly strong gravitational forces. The journey from the outer galaxy to the black hole is not easy. Gas must shed most of its angular momentum before it can approach the event horizon. Many processes can interrupt or redirect that flow. Some gas form stars before reaching the center, some remains in rotating structures, some is expelled. Only a fraction may ultimately be accreted by the black hole. Yet that fraction can still release an extraordinary amount of energy, because accretion converts gravitational energy into radiation and motion with remarkable efficiency. A relatively small amount of infalling mass can therefore influence a much larger amount of galactic gas. That imbalance between the tiny central engine and the vast host is what gives the process its evolutionary importance. It also explains why central black holes cannot be treated merely as passive objects sitting at the bottoms of gravitational wells. During active phases, they become agents within the galaxy's gas cycle. They can heat, stir, displace, and possibly remove material that would otherwise cool and form stars. They can also inject energy into the hotter atmosphere surrounding a massive galaxy, helping prevent some of that gas from cooling rapidly back toward the center. In this way, black hole activity may help maintain low star formation after a galaxy has already begun to quiet. But even here, the details remain unsettled. Observations continue to show that galaxies can contain cold gas, while forming relatively few stars, demonstrating that the presence of fuel alone does not guarantee efficient stellar birth. The real question is often not whether gas exists, but whether it can reach the right density, temperature, and dynamical state to collapse. Feedback may change those conditions without removing all of the material. This shifts the meaning of galactic decline. A galaxy does not always die because its reservoir has been emptied. It may instead become a place where the remaining gas is prevented from participating efficiently in new star formation. The central black hole is one possible part of that regulation, not a universal explanation for every quiet galaxy. Its role varies with mass environment, accretion history, and the competing influence of stars and surrounding halo gas. Even so, the connection between central activity and large-scale evolution reveals an important principle. Processes operating on very small physical scales can alter the future of structures vastly larger than themselves. The black hole can be only a minute feature in spatial terms, while its active phases reshape the conditions across an entire galaxy. And because the strongest inflows toward the center are often triggered or intensified when galaxies disturb one another, the next stage of the story moves outward again from the compact nucleus to encounters between whole stellar systems where gravity can reorganize nearly everything at once. When two galaxies begin to interact, the first changes can occur long before their bright stellar bodies appear to touch. Each galaxy sits inside an extended gravitational halo, and as those halos approach one another, their combined pull begins to reshape the motion of stars, gas, and dark matter across enormous distances. The encounter may start gently with outer material, responding first, but gravity has a way of turning a distant influence into a structural event. Tidal forces stretch one galaxy toward the other, distort disks, pull out long streams of stars and gas, and alter the orbits of material that had once moved in relatively stable patterns. If the galaxies pass close enough, the encounter can become far more disruptive. Their centers accelerate around a shifting common gravitational field, their disks can warp or overlap, and their internal structure begins to reorganize under forces that are no longer close to equilibrium. Yet the stars themselves usually pass by one another without direct collision. The distances between stars are so large compared with their physical sizes that even a dramatic galactic merger is not a crowded impact at the level of individual suns. The transformation happens because the gravitational field changes on a large scale, redirecting stellar orbits, while gas responds through an additional set of processes. Gas clouds can collide, shock compress, and lose energy. That difference makes gas especially important during interactions between galaxies rich in cold material. As the encounter disturbs their disks, some gas is driven into denser regions where gravity can overcome internal pressure more easily. Star formation then accelerates sometimes across wide regions and sometimes in a concentrated central burst. A merger can therefore produce an apparent contradiction. Large-scale disorder can create local conditions that are unusually efficient at making stars. Tidal tails may be spreading material outward at the same time that other gas is losing angular momentum and falling inward. One part of the system is being stretched while another is being compressed. The visible result can be irregular, luminous, and rapidly changing. Starburst activity is common in strongly interacting gas-rich systems because the collision rearranges the fuel, rather than merely combining two existing stellar populations. The new stars add light to a structure already being reshaped by gravity, so the galaxy seen during the encounter may bear little resemblance to either system before the interaction began. The strongest mergers can also send gas toward the central regions. Gravitational torques remove angular momentum from part of the material, allowing it to migrate inward. There, the same inflow can feed dense star formation, and under suitable conditions supply the central black holes. This creates a direct link between galactic collisions and the active galactic nucleus described earlier. A merger does not guarantee that a black hole will enter a powerful active phase, and not every active nucleus requires a major merger. but interactions can provide one efficient route for disturbing gas strongly enough to move it toward the center. The encounter can therefore influence stellar birth black hole growth and galaxy structure at the same time. Those processes unfold on different scales, yet they are connected by the same redistribution of matter and angular momentum. Major mergers in which the galaxies have broadly comparable masses can be especially transformative. If both systems contain stellar disks, their ordered rotation can be severely disrupted. Stars are thrown onto a wider variety of orbits, and after the combined system settles, the remnant may be supported more by random stellar motion than by one dominant rotating disk. This is one reason mergers between disk galaxies are considered an important pathway toward the formation of some elliptical galaxies. The connection is not a rule that every elliptical must have formed through one simple collision, nor does every merger produce the same remnant. Gas fraction orbital geometry, relative mass star formation feedback, and the possibility of later gas accretion all influence the outcome. A remnant can even rebuild a disk if enough gas survives or arrives afterward. Morphological transformation is therefore conditional rather than automatic. Still, a major merger can erase much of the previous visible organization and replace it with a new dynamical structure. The galaxy that emerges is not simply the sum of two shapes placed together. It is a system whose stars have been given new orbits, whose gas has been compressed or expelled, and whose central regions may have undergone intense activity. The long tidal features produced during the encounter gradually fade as stars disperse into the remnant or surrounding halo, but the dynamical consequences can remain for billions of years. This is why collisions function as turning points rather than brief visual disturbances. The spectacular phase may be temporary while the altered structure survives. Minor mergers operate more quietly, but can be just as important over long periods. A large galaxy may repeatedly absorb smaller companions without losing its overall identity in a single event. Each encounter adds stars' gas and dark matter, while also transferring orbital energy into the existing system. A disk can thicken, a stellar halo can grow, new streams and shells can appear. Gas from a small companion may trigger localized star formation or feed the central regions. Repeated minor mergers can gradually change a galaxy that would otherwise appear to have evolved peacefully. Their cumulative effect can rival the significance of a rarer major merger because galactic evolution extends over such long timescales. A galaxy does not need one catastrophic encounter to carry the fingerprints of collision. It may be altered through a sequence of smaller gravitational disturbances spread across billions of years. Environment affects how often these encounters occur and what form they take. In small groups, galaxies may move slowly enough relative to one another for strong interactions and eventual mergers to be common. In rich clusters, galaxies can pass one another at much higher speeds, producing frequent gravitational encounters without always becoming bound pairs that merge quickly. The surrounding gravitational potential also influences the paths of the galaxies and the behavior of their gas. Collisions therefore belong to a larger environmental story. A merger is never only an interaction between two isolated stellar systems. It happens within halos groups, filaments or clusters that shape the initial conditions of the encounter. The history of one galaxy may include periods of quiet growth, punctuated by several different kinds of collision, each occurring under different environmental circumstances. The chemistry of the remnant also becomes mixed. Stars from each progenitor retain much of the chemical record of where they formed, while gas can be redistributed and enriched by the new star formation triggered during the encounter. Later observations may reveal multiple stellar populations with different ages and compositions evidence that the final system was assembled from components with separate histories. The merger destroys some forms of order while preserving others as hidden memory. A smooth elliptical galaxy can look visually simple, even though its stars carry a complicated ancestry. The absence of obvious tidal features does not mean the absence of previous collisions. Those structures fade. But the orbital and chemical evidence can remain. This is one reason studying galaxy evolution requires more than photographing shapes. Motions, ages, compositions, faint outer structures, and central activity all help reconstruct what a merger has changed. The collision also alters the future supply of star-forming gas. A burst of stellar activity can consume part of the cold reservoir rapidly. Supernovae and central black hole activity can heat or displace additional material. Some gas may be thrown into extended tails, some may remain bound in the halo, and some may later fall back toward the remnant. The encounter can therefore both stimulate star formation and help prepare the conditions for its later decline. That sequence is important because mergers are sometimes associated with galaxies moving from actively star-forming states toward quieter ones, but the relationship is not universal. A collision can trigger new stars without permanently shutting the system down. If enough cold gas remains or fresh gas arrives, later star formation can continue. The same event can produce different long-term outcomes depending on the wider supply of material and the strength of feedback. Galactic collisions are therefore not simply acts of destruction. They are mechanisms of redistribution. They move matter inward and outward, reorder stellar orbits, build halos, feed starbursts, influence black holes, and sometimes transform morphology completely. In a universe where structures grow hierarchically, mergers are not rare accidents superimposed on otherwise isolated evolution. They are part of the normal way galaxies become larger and more complex, yet the most dramatic collisions represent only one end of that process. Much of a massive galaxy's growth can occur through smaller companions whose disappearance is quieter, leaving behind thin streams and diffuse populations instead of one obvious remnant. The next stage of galactic life is written in those faint traces where the evidence of consumption can survive long after the swallowed galaxy itself has lost its name. The remains of a small galaxy do not always vanish when the galaxy itself loses its identity. Long after a satellite has been pulled apart by a larger neighbour, its stars can continue moving through the host, as narrow streams diffuse shells, extended arcs or faint populations spread across the outer halo. These structures are the quieter signatures of galactic cannibalism, the gradual process by which large galaxies continue growing through the absorption of smaller companions. Unlike a major merger which can transform the appearance of a galaxy over a comparatively short interval, the capture of a dwarf or low-mass satellite can unfold slowly enough that the larger system seems almost undisturbed from a distance. The smaller galaxy enters the extended dark matter halo of the larger one, begins orbiting within its gravitational field, and is subjected to tidal forces that become stronger as it approaches the central regions. Those forces act unevenly across the satellite. Stars and dark matter on the near side feel a slightly different gravitational pull from material on the far side, and over repeated passages, the difference can stretch the satellite and remove material from its outskirts. The process is often gradual. The companion may survive several orbits while losing mass each time it passes near the host. Eventually, the object can be reduced to a dense remnant surrounded by trails of stars that once belonged to it. If disruption continues, even that remnant may dissolve, leaving only the orbital memory of a galaxy that no longer exists as a distinct system. These stellar streams are valuable because they preserve information that the smooth appearance of a mature galaxy can hide. Stars moving together along an elongated path often share an origin, and their chemistry, ages, and motions can reveal that they formed inside a smaller system before being incorporated into the larger host. The stream is therefore not simply debris. It is an archaeological record, By tracing these remnants, astronomers can reconstruct parts of the merger history that would otherwise be invisible. The outer regions of large galaxies are especially useful for this purpose, because they are less densely populated than the central disk or bulge, allowing coherent structures to remain recognizable for longer. Over time, however, even streams disperse. Their stars follow slightly different orbits spread around the host and gradually blend into a more diffuse stellar halo. The evidence becomes harder to see, but the accreted stars remain. In this way, a large galaxy can contain material from many destroyed systems without displaying an obvious boundary between them. Galactic identity becomes layered. Some stars are born within the main body of the galaxy, while others arrive after spending much of their earlier existence somewhere else. The distinction is not visible to the eye, but it can survive in motion and chemical composition. A star accreted from a small dwarf may carry lower abundances of heavier elements than a star of similar age that formed within a more massive host, because smaller galaxies often follow different histories of chemical enrichment. Groups of stars sharing unusual chemical patterns and similar orbits can therefore point toward a common disrupted ancestor. The stellar halo of a large galaxy is not simply a random cloud of ancient stars. Part of it may be assembled piece by piece from the remnants of former satellites. This makes the halo a kind of historical archive, though one that is incomplete and constantly being mixed. Each new merger adds another layer. Some accreted systems contribute only a small number of stars. Others deposit enough material to create prominent structures that dominate portions of the outer halo. The total effect depends on the mass of the satellites, the timing of their accretion, and the orbits along which they were captured. A satellite that falls in recently may leave a sharp, narrow stream. One absorbed much earlier may be so thoroughly mixed that only subtle chemical and dynamical patterns remain. A relatively quiet-looking galaxy can therefore have a surprisingly active past. Its disk may appear stable, its spiral arms may show no obvious sign of major disruption, yet its outskirts can contain the accumulated evidence of repeated minor mergers. This is one reason galactic evolution cannot be divided neatly into violent systems and peaceful ones. Growth through cannibalism occupies a middle ground. Each individual event may be modest, but the combined effect across billions of years can be substantial. The host gains stars' dark matter and sometimes gas. Its stellar halo becomes more massive. Its disk can be heated and thickened. Its central regions may receive material transported inward by gravitational disturbances. Its dark matter distribution is altered by every new satellite that enters and loses orbital energy. The larger galaxy changes even when its overall shape survives. The swallowed companion changes more completely, but it also influences the system that consumes it. Gas-rich satellites can bring fresh star-forming material into the host. That gas may be stripped before the satellite reaches the center, joining the larger galaxy's halo or disk. In other cases, gas can be compressed during the interaction and form stars before the merger is complete. A satellite that has already lost most of its gas contributes mainly stars and dark matter, producing a different kind of accretion event. Galactic cannibalism is therefore not one uniform process. Its consequences depend on what the smaller galaxy carries with it and how deeply it penetrates before disruption. Even the orbit matters. A companion moving roughly with the rotation of a disk can interact differently from one arriving on a steeply inclined or nearly opposite trajectory. The distribution of deposited stars reflects these details, creating streams, shells, plumes, and diffuse structures whose shapes can preserve clues to the encounter. The process also extends the hierarchical growth that began before galaxies were fully formed. Small dark matter halos merged into larger halos in the early universe, and the galaxies that developed inside them later continued the same pattern on visible scales. A present-day massive galaxy is therefore not simply an ancient object that grew steadily from one original seed. It is a composite system assembled through many channels. Some of its material arrived as diffuse gas. Some formed into stars locally. Some entered already locked inside smaller galaxies. The relative importance of these pathways changes with time and from one galaxy to another. In the outer regions, especially, accreted stars can become a significant fraction of the population, making the faint halo a record of external growth. This record also shows that mergers do not need to erase a galaxy to transform it. A disk can survive repeated minor encounters while becoming thicker, dynamically hotter, and more populated by stars that did not form within it. A bulge can gain mass. A halo can expand. Satellite systems can be reorganized as new companions arrive and old ones disappear. The galaxy remains recognizable, but the meaning of its structure changes. What looks like one continuous body is actually the accumulated outcome of many separate histories. Over sufficiently long periods, the distinction between native and accreted material can become blurred almost completely. Stars do not retain labels identifying where they began. Gravity mixes them through the host. Only careful measurements of motion age and composition reveal the underlying complexity. This gives galactic archaeology its importance. By examining stellar populations in detail, astronomers can work backward from present structure toward vanished events. A stream suggests a recent disruption. A chemically distinct population may indicate an older merger. A smooth outer halo may contain the mixed remains of several systems whose original forms can no longer be recovered individually. The reconstruction is never perfect because gravitational mixing erases information over time, but enough survives to show that cannibalism is a normal part of galactic growth, rather than an exceptional episode. The process also connects directly to the fate of the smaller galaxies themselves. A satellite may lose gas before it loses stars. Environmental effects inside the larger halo can weaken its ability to form new stars even while it continues orbiting intact. Tidal forces can then strip the remaining stellar body, completing a decline that began before full disruption. In this way, accretion and quenching can become linked. The galaxy being consumed may stop forming stars because its gas supply is removed or restricted, then later dissolve into the host. The larger galaxy gains its old stars, but not necessarily a large supply of fresh star-forming fuel. Repeated events of this kind can increase stellar mass without restoring much new star formation. That distinction becomes increasingly important as galaxies mature. Growth in mass and growth in star formation do not have to continue together. A large galaxy can keep absorbing companions after its own most active star-forming era has ended. It can become larger while becoming quieter. The history of cannibalism therefore leads naturally toward a deeper question about galactic aging. If galaxies can continue accumulating stars while producing fewer of their own, then the end of star formation cannot be understood simply as the end of growth. Something more specific must happen to the cold gas and to the conditions that allow that gas to collapse. The stellar streams reveal where previous galaxies went. The next problem is to understand why in many mature systems, the creation of new stars begins to fade even while plenty of matter remains gravitationally bound. Star formation begins to fade when a galaxy can no longer keep enough gas in the cold, dense state required for gravitational collapse. But that simple statement hides several very different physical pathways. A galaxy may still contain enormous amounts of matter and yet produce new stars only weakly. It may retain old stars' hot gas, dark matter, a central black hole, and even reservoirs of cold material, while the birth of new stellar populations slows almost to a halt. Astronomers describe this state as quiescent or quenched terms that refer to suppressed star formation rather than the disappearance of the galaxy itself. The transition matters because it marks a fundamental change in galactic evolution. Earlier stages are dominated by accumulation cooling and the conversion of gas into stars. Quenching begins when that conversion loses efficiency or when the supply chain supporting it is disrupted. One possible route is gradual exhaustion. Stars form from dense molecular gas, so a galaxy that continues consuming its available cold material without receiving enough replacement will eventually reduce its star formation rate. Yet complete fuel exhaustion is rarely the only process worth considering. Gas can be present, but too warm, too diffuse, too turbulent, or too poorly compressed to form stars efficiently. Fresh material can also be prevented from reaching the disk, even while substantial gas remains elsewhere in the halo. The critical issue is not merely whether a galaxy possesses gas, but whether that gas can continue moving through the sequence that leads from a diffuse reservoir to dense star-forming clouds. Heating provides one way to interrupt that sequence. As gas falls into a sufficiently massive halo, it can be shock heated to high temperatures and form an extended atmosphere around the galaxy. Hot gas has greater pressure support and can remain diffuse for long periods rather than cooling quickly toward the central regions. If cooling becomes inefficient, the galaxy is effectively cut off from the steady replenishment that once supported its star-forming disk. The existing cold gas may continue producing stars for a time, but without sustained inflow, the reservoir declines or becomes increasingly difficult to use. This pathway is sometimes described as starvation, because the galaxy is not stripped of everything at once. Instead, the supply line is weakened. The decline can take a long time, leaving a period in which star formation gradually falls while the stellar population continues aging. In massive systems, the central black hole may reinforce this process. Energy released during active phases can heat surrounding material, drive winds, or inject energy into the hot atmosphere of the halo. If that energy prevents gas from cooling efficiently, it can help maintain a quenched state even after the initial decline has begun. This form of feedback is attractive in models because a massive galaxy may otherwise have enough surrounding gas to resume star formation repeatedly. A central source of energy offers a way to keep part of that reservoir from returning rapidly to the cold phase. Still, the mechanism is not perfectly understood, and not every quiet galaxy provides the same evidence for strong black hole activity. Feedback may be episodic, indirect, or more effective at maintaining quiescence than initiating it. The distinction is important. A process that prevents a galaxy from restarting star formation does not necessarily have to be the same process that caused the first decline. Stellar feedback can also contribute, especially in smaller galaxies. Massive young stars' winds and supernova explosions inject energy and momentum into surrounding gas. In a shallow gravitational potential, some of that material can be pushed out of the star-forming regions or even expelled from the galaxy more completely. This reduces the supply available for future stellar birth. Yet feedback from stars is also part of normal active star formation, so its effect depends on the ability of the galaxy to retain and recycle what has been displaced. A massive system may keep much of the gas gravitationally bound, while a small dwarf can lose a larger fraction. The same physical process, therefore, has different evolutionary consequences depending on the depth of the halo. Another route to quenching involves preventing gas from becoming gravitationally unstable, even when it remains cold. A galaxy can contain molecular material without forming stars at the rate expected from the amount of fuel alone. Turbulent shear magnetic effects, changing pressure, or the dynamical structure of the galaxy can make collapse less efficient. A growing central bulge, for example, can alter the gravitational environment of the gas and help stabilize portions of a disk against fragmentation under some conditions. The details vary, but the broader lesson is that cold gas is a requirement for ordinary star formation, not a guarantee of it. This has become increasingly important as observations identify quenched galaxies that still contain substantial cold gas reservoirs. Such systems challenge the simplest picture in which galactic death follows only after the fuel tank has been emptied. If the raw material remains, then the suppressed star formation must also involve the physical state distribution or stability of that material. The problem shifts from asking where the gas went to asking why the gas has stopped behaving like efficient stellar fuel. That change sharpens the scientific puzzle rather than resolving it. Some galaxies may be quenched because gas was removed. Others may be quenched because gas was heated. Still others may retain cold material that no longer collapses efficiently. Several mechanisms can operate together, and the dominant pathway may depend on stellar mass-halo mass, merger history, central black hole activity, and environment. This variety helps explain why quenching remains an open research problem rather than a single settled stage in a universal galactic life cycle. The transition can also occur at different rates. Some galaxies appear to reduce star formation relatively quickly, perhaps following a major disturbance, intense central activity, or abrupt environmental influence. Others decline gradually as their gas supply becomes less effective over much longer intervals. These different timescales leave different signatures in the stellar populations. A rapid shutdown can preserve a clearer separation between stars formed before and after the transition, while a slow decline produces a more extended sequence of aging populations. By studying stellar ages and the remaining gas, astronomers can estimate how the activity changed, although reconstructing the exact cause from the present state remains difficult. Several mechanisms can lead to similar visible outcomes. A red quiet galaxy does not announce whether its decline began through starvation, feedback, environmental stripping, internal stabilization, or some combination of them. The history must be inferred from additional evidence. Even the word death can therefore be misleading. Quenching is not the destruction of a galaxy. Gravity still binds its stars. Stellar remnants continue orbiting. Low-mass stars can shine for extraordinary spans of time. Satellites may still fall inward, and mergers may continue adding stellar mass. A quenched galaxy can grow structurally while forming very few new stars of its own. It may even acquire new gas later, though. Whether that gas can restart significant star formation depends on the state of the system. Quiescence is a change in metabolism rather than an end to existence. The galaxy remains dynamic, but one of the processes that once defined its youth has weakened. This changes its light because the most massive blue stars disappear rapidly when they are no longer being replaced. It changes its chemistry because fewer new generations are forming from enriched gas. It changes the balance between the stellar population and the interstellar medium. Yet none of these changes happens at one precise instant. A galaxy crosses into quiescence through a decline whose boundaries are defined observationally rather than by a single physical moment. The underlying causes can begin long before the galaxy is classified as quenched. A hot halo may have been restricting fresh inflow for a long period. A central black hole may have undergone several active episodes. A merger may have redistributed the gas. The cold reservoir may have been gradually stabilized or depleted. By the time star formation becomes visibly weak, the process may already have a long history. The central mystery is therefore not why galaxies eventually consume some of their gas. That is inevitable wherever stars form. The deeper problem is how some systems lose the ability to convert available matter into new stars while others remain active for much longer. Quenching marks the point where galactic evolution stops being primarily a story of acquiring fuel and becomes a story of regulating access to it. And in many galaxies, the decisive regulation does not come from the galaxy alone. The surrounding group or cluster can alter the supply-remove gas and change the conditions of survival from outside, turning environment itself into an agent of decline. A galaxy does not evolve only according to what happens inside it. The larger environment can alter its gas supply, distort its structure, change its orbit, and gradually suppress the very conditions required for new stars to form. This becomes especially important when a galaxy moves from relative isolation into a group or cluster where it encounters not only other galaxies, but also a much denser surrounding medium and a deeper collective gravitational field. In such places, galactic evolution becomes partly environmental. The galaxy may arrive with a rotating disk rich in cold gas and an active population of young stars, yet over time the surroundings can remove that gas, prevent new material from arriving, or heat it into a state that is difficult to use. The result can be quenching, driven from outside rather than primarily by the galaxy's own black hole stellar feedback or internal dynamics. One of the clearest mechanisms is ram pressure stripping. A galaxy traveling through the hot diffuse gas that fills a massive cluster experiences pressure from that medium much as an object moving through a fluid experiences resistance. The stars and dark matter of the galaxy are affected mainly by gravity, but the gas can be pushed directly. If the pressure becomes strong enough, loosely bound gas in the outer regions can be swept away from the disk. The effect can produce long tails of stripped material extending behind the galaxy, leaving a visible record of gas loss while the stellar component remains comparatively intact. The galaxy is not torn apart in the same way as during a major merger. Instead, one of its most important resources is selectively removed. Star formation may continue for a time in the inner regions where gas is more tightly bound, but the outer disk can become quiet first. The decline therefore moves through the galaxy spatially as well as through time. The environment does not always need to remove existing cold gas directly. It can also cut off the future supply. A galaxy entering a larger halo may once have drawn fresh material from the cosmic web or from its own surrounding reservoir. Inside a group or cluster, that connection can weaken. Gas associated with the galaxy's halo may be stripped away, heated, or absorbed into the larger environment. Without this extended reservoir, the galaxy can continue forming stars only from what is already available in its disk. As that material is converted into stars heated or expelled, replenishment becomes increasingly limited. This slower process is often described as starvation or strangulation. The name reflects the gradual nature of the decline. Nothing needs to happen suddenly. The galaxy can remain recognizable for a long period, while its capacity for renewal quietly decreases. Its star formation rate falls not because every cold cloud disappears at once, but because the system can no longer replace what it uses. Groups can be especially important environments for this kind of evolution, because galaxies may spend substantial time there before ever entering a richer cluster. A galaxy can therefore begin changing long before it reaches the densest environment visible around it. This creates a layered history in which environmental processing occurs in stages. A satellite may first lose part of its outer gas in a group, then later experience stronger stripping after the group itself becomes part of a cluster. By the time the galaxy appears deeply quenched, the relevant environmental history may extend across several different gravitational settings. This makes present location an imperfect guide to cause. A quiet galaxy near the center of a cluster may have started losing its gas much earlier, while another galaxy farther from the center may already have passed through the dense interior on a previous orbit. Environment has memory because orbital history matters. The collective gravity of a group or cluster also influences galactic structure. As a galaxy moves through a changing gravitational field, tidal forces can disturb its outer stars and gas. Close passages with neighboring galaxies add further perturbations. In dense regions, repeated high-speed encounters may not lead immediately to mergers, but they can still alter disks, redistribute stars, and weaken loosely bound material. Over time, these effects can make a galaxy more dynamically disturbed, even when no single encounter appears decisive. The environmental transformation can therefore combine several modest influences rather than one dramatic event. Gas-stripping tidal interactions, restricted accretion, and internal feedback may operate together, each changing the conditions under which the others act. A galaxy that has already lost some of its gas becomes more vulnerable to further decline. A disk disturbed by tidal forces may move gas inward, briefly increasing central star formation before the remaining supply weakens. A central black hole may become active during that period and help heat or displace additional material. The environment does not replace internal evolution. It changes the setting in which internal processes operate. This overlap is one reason assigning a single cause of quenching can be difficult. Several mechanisms may leave similar final states, and the mechanisms themselves can reinforce one another. The mass of the galaxy matters as well. A low-mass galaxy generally has a shallower gravitational well, making its gas easier to remove. A more massive system can hold on to dense central gas more strongly, even while its outer reservoir is stripped. The same cluster environment can therefore produce different outcomes depending on the galaxy that enters it. Orbital path matters too. A galaxy passing rapidly through the dense central regions may experience stronger ram pressure than one remaining farther out. The density of the surrounding intra-cluster gas matters. The orientation of the galactic disk matters. The amount of gas already present matters. Environmental quenching is therefore not a uniform fate delivered equally to every member of a cluster. It is a process shaped by motion, mass structure, and timing. This variability also explains why some cluster galaxies remain actively star-forming, while others nearby are already quiescent. Environment raises the probability of transformation, without dictating an identical history for all systems. The observational pattern is nevertheless clear enough to show that surroundings matter. Dense environments contain larger populations of galaxies with suppressed star formation than more isolated regions, and this connection has become one of the central clues in understanding how galactic life depends on context. A galaxy is not simply born, grows and fades according to an internal clock. Its trajectory can change when it crosses into a new gravitational and gaseous environment. The cosmic web that once supplied material can lead it into a group. The group can later join a cluster. Each transition changes what gas can be retained and what fresh material can still arrive. The same large-scale structure that helped build galaxies can eventually contribute to limiting them. There is a quiet symmetry in that progression. Early in cosmic history, dense regions are places where matter gathers efficiently and galaxies grow rapidly. Later, those same dense environments can become places where interactions are frequent. Hot gas is abundant and the supply of cold star-forming material is harder to maintain. Growth and suppression emerge from the same underlying architecture at different stages. Even then, environmental quenching is not equivalent to destruction. A stripped galaxy may continue orbiting the cluster for billions of years. Its old stars remain bound. Its dark matter halo may be reduced but not eliminated. Its central black hole remains. It may continue to merge with smaller companions or be altered by future encounters. What changes most fundamentally is the balance between old stars and the formation of new ones. As the young stellar population stops being replaced, the galaxy's light begins to shift. Massive blue stars disappear first because their lives are comparatively short. Longer-lived cooler stars become increasingly dominant. The system grows redder and quieter, even while billions of stars continue moving through it. By this stage, the phrase galactic death becomes especially misleading. The galaxy is still there, still gravitationally active, still carrying the record of every merger, every stripped cloud, every vanished satellite, and every star-forming episode that came before. What has ended is not the galaxy itself, but its youthful capacity for continual renewal. The environmental story therefore hands the galaxy into a new Phase 1, in which aging stellar populations define its appearance and the absence of fresh blue stars becomes more visible than the processes that cause their disappearance. A quenched galaxy can look quiet enough to suggest that little is happening, but its apparent stillness is deceptive. Billions of stars continue moving through the gravitational field. Old stellar populations continue to age, remnants continue to orbit, and the galaxy remains part of the larger network of interactions and mergers around it. What has changed is not the existence of the system, but the balance of its light. When star formation declines sharply, the short-lived massive stars that once contributed strongly to blue and ultraviolet wavelengths are no longer replaced in large numbers. Those stars disappear comparatively quickly, ending as compact remnants or releasing material back into the surrounding medium, while lower mass stars continue shining for much longer periods. As a result, the integrated light of the galaxy shifts toward the redder colors, associated with older stellar populations. This is the origin of the familiar phrase red and dead, but the phrase compresses a complicated evolutionary state into something more final than the physics really allows. Red describes the changing stellar population reasonably well in many cases. Dead is only shorthand for very weak ongoing star formation. The galaxy itself remains dynamically alive. Its stars cross enormous orbits. Its central black hole may still experience episodes of activity. Satellite systems may continue to evolve around it, and new encounters can alter its structure long after the main era of stellar birth has ended. The transformation in color is especially revealing because it is driven by stellar lifetimes. Massive blue stars consume their nuclear fuel rapidly. Their brilliance comes at the cost of short lives, so a galaxy forming many of them must continue producing replacements if it is to remain visibly blue. Once star formation falls, that replacement cycle weakens almost immediately on galactic timescales. The blue population fades first. Stars with lower masses and cooler surfaces survive much longer, and their accumulated light becomes more important. The galaxy therefore changes appearance even if its total stellar mass hardly changes at all. This makes color a kind of clock, though not a perfect one. Dust can redden an actively star-forming galaxy, and stellar populations can contain mixtures of ages and compositions, so appearance alone cannot determine evolutionary state with certainty. Astronomers combine color with spectra gas measurements, stellar ages, and other evidence to distinguish between a genuinely quiescent system and one that is merely obscured or temporarily subdued. The deeper point remains that a quiet galaxy is dominated by memory. Most of its visible stars formed during earlier periods when gas was more readily converted into new stellar populations. Their light is the delayed consequence of past star formation, rather than evidence of strong activity in the present. This gives quiescent galaxies a different relationship with time. An actively star-forming system is continuously renewing its luminous population. A quenched galaxy becomes increasingly dependent on stars that already exist. Each passing interval changes the balance as those stars evolve according to their masses. Some leave the main sequence and swell into later stages of stellar evolution. Some shed their outer layers. Some end as white dwarfs. More massive survivors from earlier epochs become neutron stars or black holes. The galaxy gradually fills with a growing population of remnants, even while long-lived stars continue to provide visible light. None of this requires new star formation. Stellar evolution alone ensures that a quenched galaxy remains physically active over enormous timescales. The gas also does not necessarily vanish. Some quiescent galaxies retain molecular or atomic material, sometimes in substantial quantities, yet form stars inefficiently. This reinforces the distinction between possessing fuel and being able to use it. Gas may be distributed too diffusely stabilized against collapse, heated intermittently disturbed by internal motions, or prevented from reaching the densities needed for efficient star formation. In such a system, the old stellar population can dominate the light, while a reservoir of potentially useful material remains hidden within or around it. The galaxy is therefore not always empty after quenching. It can instead become inefficient. The machinery of stellar birth is reduced without every component of that machinery being removed. This is one reason the study of quiescent galaxies remains closely tied to the unresolved problem of quenching itself. Their present condition contains clues to the processes that suppressed star formation, but those clues are often ambiguous. A galaxy with little cold gas may have lost or consumed much of its supply. Another with abundant cold material must have been suppressed in a different way. A third may have experienced several mechanisms in sequence. By the time the galaxy becomes fully dominated by old stars, the original cause may be difficult to reconstruct from appearance alone. Structure provides additional evidence. Many quiescent galaxies are elliptical or lenticular forms, often associated with older stellar populations and reduced cold gas, but morphology and star formation are not locked together perfectly. A disk can remain visible after star formation has largely ceased. An elliptical system can occasionally acquire gas and form new stars. A merger can change morphology without immediately producing permanent quenching, while quenching can occur without destroying a disk. This separation matters because galactic evolution does not follow one universal track from blue spiral to red elliptical. Some systems do move through broadly similar transformations, but others preserve their structure while their stellar populations age. Shape and star formation history are connected, yet neither determines the other completely. A quiet galaxy can also continue gaining mass through mergers. If it absorbs a smaller companion that contains mostly old stars, its stellar mass increases without significantly restoring star formation. This kind of merger is sometimes called dry because relatively little cold gas participates. Such encounters can build the outer regions of massive quiescent galaxies and alter their size even after their main star-forming phase is over. Growth therefore continues after quenching, but its character changes. Earlier growth may have been strongly tied to gas accretion and the formation of new stars. Later growth can be dominated increasingly by the addition of stars that formed elsewhere. The galaxy becomes larger without becoming younger. Even a gas-rich companion does not guarantee lasting rejuvenation. Fresh material may trigger a limited period of star formation, but the same conditions that maintained quiescence may eventually suppress it again. A hot halo can still inhibit replenishment. Central black hole activity can still influence the gas. Environmental effects can still strip or heat incoming material. A galaxy that has become quiescent is therefore not sealed permanently into one state, but neither is renewal easy. Its later evolution depends on whether enough suitable gas can reach dense regions and remain there long enough to form stars efficiently. In many massive systems that becomes increasingly difficult, their old stellar populations can then persist for billions of years, while the galaxy participates in a slower form of cosmic evolution. This changes what death means on the scale of a galaxy. There is no final heartbeat, no single moment when the system crosses from existence into absence. The decline is statistical and gradual. Star formation drops. The youngest luminous stars disappear. The spectrum shifts. The average stellar age increases. Remnants accumulate. New stars become rare. Yet gravity continues binding the system, and interactions continue revising it. Even the phrase quiescent carries this ambiguity. It describes low activity in one important process while leaving many others untouched. A galaxy can be quiescent and still merge. It can be quiescent and still contain gas. It can be quiescent and still host a central black hole. It can be quiescent and still evolve structurally. The apparent simplicity of an old red galaxy therefore hides a layered history of formation, feedback, collision, stripping, and stellar aging. Its current light is a compressed record of all those earlier phases. As cosmic time continues, more of that record shifts toward increasingly long-lived stars and stellar remnants. The galaxy does not vanish when the blue stars are gone. It simply enters a state in which renewal is no longer the defining process. From that point onward, its future is governed less by the rapid creation of luminous populations and more by the slow aging of what remains, the mergers still to come, and the gradual depletion of opportunities for new stars to form at all. The final fate of a galaxy is not decided when star formation first becomes quiet. Long after the last major burst of stellar birth, the galaxy continues changing through processes so slow that on human timescales they appear almost frozen. Existing stars age according to their masses. Some galaxies continue merging with neighbours. Stellar remnants accumulate. Gas becomes harder to cool, harder to concentrate, or simply too scarce to sustain much new activity. The bright structured systems familiar from the present universe therefore move not toward one sudden ending, but toward an extended era of decline in which fewer and fewer processes are capable of restoring their former youth. In the near cosmic future, mergers remain one of the strongest agents of change. Galaxies that are gravitationally bound within groups can continue approaching one another, even as the expansion of the universe increases the separation between more distant systems. The local gravitational relationship matters more than the general expansion on these scales. As a result, some galaxies that are separate today may eventually combine into larger remnants. The Milky Way and Andromeda, for example, are part of the same local gravitational environment, and their long-term evolution illustrates a wider principle. Galactic structure is temporary, even when individual galaxies appear stable for billions of years. Future mergers can destroy recognizable spiral patterns, scatter stars onto new orbits, combine central black holes, and redistribute whatever gas remains. Yet the collisions will still not resemble impacts between solid bodies. Most stars will pass one another at enormous distances. The transformation will occur through gravity orbital reshaping, gas dynamics, and the gradual settling of the remnant. As repeated mergers continue within bound groups, the number of distinct galaxies can decrease even while the surviving systems become more massive. Some of those future remnants may contain enormous populations of old stars assembled from several earlier galaxies, turning former neighbours into different layers of the same object. This process changes galactic identity long after active star formation has weakened. A galaxy can therefore lose its original shape and name without disappearing physically. Its stars remain, but they belong to a new gravitational structure. At the same time, the stellar populations inside these remnants continue aging. Massive stars are already short-lived compared with the history of a galaxy, so they disappear early once star formation stops. Intermediate mass stars follow later, leaving white dwarfs and enriching the surrounding space with material shed during their final stages. Lower mass stars persist much longer. Red dwarfs, small and efficient at using their nuclear fuel, can survive for extraordinarily long periods compared with stars like the Sun. Over the distant future, galaxies increasingly become dominated by these faint, long-lived stars and by the remnants of stars that have already completed their luminous evolution. White dwarfs, neutron stars, and stellar mass black holes gradually make up a larger share of the compact population. The galaxy still contains matter in abundance, but a decreasing fraction of that matter participates in bright stellar activity. The luminous appearance fades even though the gravitational structure remains. Residual gas can delay this transition in places. A merger may bring fresh material into an otherwise quiet system. Cooling within some regions may allow limited new star formation. Gas expelled during earlier phases can sometimes return. But these episodes become increasingly difficult to sustain if the larger supply of cold material is not renewed. Star formation steadily converts usable gas into stars, while feedback heating environmental effects and black hole activity can keep other gas away from the dense conditions needed for collapse. Over sufficiently long timescales, the opportunities for major episodes of stellar birth become rarer. The universe does not need to remove every atom of gas for galaxies to grow old. It only needs to reduce the fraction of gas that can become cold and dense enough to create new stars efficiently. This distinction means that the fading of galaxies is fundamentally a decline in organized activity. Matter remains, but fewer pathways remain available for turning that matter into young luminous populations. Central supermassive black holes also persist through this transformation. When galaxies merge, their black holes can eventually form bound pairs and may ultimately combine, although the detailed pathway can be complex. The resulting black hole becomes more massive while the surrounding galaxy becomes older. During earlier eras, abundant gas could feed bright, active galactic nuclei. In a far more gas-poor future, such episodes should become less common. A black hole without an ample inflow remains gravitationally important near the center, but radiatively quiet. The most energetic phases of galactic life therefore fade alongside star formation. The galaxy moves toward a state in which enormous masses are present, but little of that mass is releasing energy in dramatic ways. Even then, gravity continues rearranging the system slowly. Encounters between stars can alter orbits over immense periods. Compact objects can sink towards central regions through gravitational interactions. Some stars can be scattered onto trajectories that carry them far outward, while others remain bound within increasingly diffuse remnants. The structure that survives is no longer maintained by active stellar renewal, but by the long-lived gravitational relationships between objects formed much earlier. As cosmic expansion continues, the environment around bound galactic groups changes as well. Distant galaxies that are not gravitationally bound recede ever farther away. Over enormous spans of time, cosmic expansion can carry many external galaxies beyond practical visibility from any one bound region, leaving local remnants increasingly isolated from the broader observable population. The universe at that stage would not be empty, but it would appear far less connected. A future galaxy remnant might contain the accumulated stars of several present-day systems, while the light from distant cosmic structure becomes progressively harder to receive. The large-scale universe therefore becomes more separated at the same time that locally bound galaxies complete their mergers. These two tendencies move in opposite directions: consolidation nearby and isolation on larger scales. Within the remnants, the longest-lived stars continue shining after most familiar stellar populations have vanished. Eventually, even those stars exhaust their fuel. The luminous era of a galaxy then gives way increasingly to one dominated by stellar remnants. White dwarfs cool. Neutron stars become harder to detect. Black holes remain dark unless matter happens to fall toward them. The system is still composed of objects with mass and motion, but the amount of visible light falls dramatically. At such distances in time, the term galaxy itself becomes less intuitive. The present definition is tied partly to bound collections of stars, gas dust, dark matter, and related structures. A remote future remnant may preserve the gravitational ancestry of a galaxy, while containing almost no active star formation and very little bright stellar light. It would be a fossil not merely in the ordinary astronomical sense, but in a deeper temporal one, a structure whose defining events occurred unimaginably long before. No single moment marks when that transformation becomes complete. One star dies, while another remains. One pocket of gas forms a final small generation of stars while another stays diffuse. One merger reshapes the system while distant companions continue on separate paths. The end comes through decreasing frequency rather than a final event. Star formation becomes rarer. bright massive stars disappear. Gas loses access to the conditions needed for collapse. Mergers within bound environments eventually leave fewer separate systems to combine. Active galactic nuclei become uncommon as fuel becomes scarce. Stellar remnants become increasingly dominant. Each stage closes one pathway while leaving others open for longer. This is why galactic death is better understood as a long evolutionary fading than as destruction. The stars do not all switch off together, and the galaxy does not dissolve at the instant it becomes quiescent. Its youth ends first. Its bright stellar populations follow. Its structure continues changing. Its remnants endure. What began as a slight density excess in the early universe becomes over billions upon billions of years an immense gravitational archive containing the consequences of gas accretion, star formation, dark matter, assembly, black hole growth collisions, cannibalism, quenching and stellar aging. The life of a galaxy is therefore not a path from existence to non-existence, but from possibility to structure, from structure to activity, and from activity into memory. Its final state is not defined by one death, but by the gradual disappearance of the processes that once allowed it to renew itself. The life of a galaxy stretches across timescales so large that beginnings and endings become difficult to separate. What starts as a slight unevenness in the early universe becomes dark matter, halo, then a gathering place for gas, then a nursery for stars, a structure shaped by rotation collisions, black holes, and the long exchange of matter with its surroundings. For a time the galaxy can seem intensely alive, bright with young stars and restless with change. Later that activity softens. Gas becomes harder to use. New stars appear less often. Older populations come to dominate the light. Yet even then the galaxy continues. Its stars remain in motion. Its remnants preserve earlier generations. Its outer halo carries traces of smaller systems that once existed independently. Its structure may still be revised by mergers long after its most active era has passed. In that sense, a galaxy never has one simple age and never reaches one simple death. It is a layered history held together by gravity. Every stage contains evidence of what came before, from the invisible framework that first gathered matter to the faint stellar populations that survive after star formation has nearly ended. Over the far future, the bright eras gradually give way to quieter ones, and the universe becomes increasingly dominated by long-lived stars' remnants and structures whose greatest transformations happened deep in the past. The story does not close with disappearance, but with fading activity and enduring memory. Galaxies begin as possibilities written into the distribution of matter, grow into immense systems of stars and gas, and eventually settle into slower forms of existence. Their secret life is not hidden because nothing can be known about it. It is hidden because almost all of it unfolds too slowly